Hey folks, Dr. Tom McNamara here again for our course in trigonometry. I'm going to use the document camera for some of these problems here. So the key ideas for this video are the concepts of linear velocity and angular velocity. And I would just like to make a note right here at the outset about some variable names. When you see the variable s, that's going to let us know we're talking about distance traveled. We use s for two reasons. One, it comes from the Latin word for distance, spatium. And number two, the letter D is used for a very important operation in calculus. So we don't want to confuse those two things. So S is going to stand for distance, T is for time, V is linear velocity, and this letter, it looks a little bit like a W, it's actually a Greek letter, it's an omega. That's going to stand for angular velocity. Okay, so let's just do a couple of examples to make sure we understand the nuts and bolts of what's going on here. Okay, now the relationship between linear velocity, distance traveled, and time is this right here. The linear velocity is the distance traveled divided by the elapsed time. And if you know any two of the variables, you can figure out the third. Okay, so let's do just a couple of quick ones here. So we'll do examples. One, if, let's say S equals 10 feet and T equals 2 minutes. We're going to find V. Okay, so that's easy enough. V equals S divided by T. 10 feet divided by 2 minutes. Okay, so 5 feet per minute. Okay, note that the units of your measurements tell you the units that your velocity will have. So we're imagining we had an object that moved 10 feet. It took 2 minutes to do that. So the object is moving at a rate of 5 feet per minute. Okay, let's switch things up a little bit. Let's imagine that something is moving at a velocity of 21 miles per hour. And that object is allowed to go at that rate for 20 minutes. We're going to find the distance traveled. We're going to find S. Okay, now this is something that you'll sometimes have to do with these types of problems. Notice the velocity is in miles per hour. So since velocity is in miles per hour, we should convert the time to hours. Okay, so in other words, these two units need to be compatible. If you're talking about miles per hour, you should have time in hours. If you're talking about feet per minute, then you should have time in minutes. Okay, so 20 minutes. And now there's 60 minutes per hour. So actually, okay, let me do it this way. 20 minutes, and then 1 hour, 60 minutes. When I'm doing conversions, I like to think of it like this. I put the units this way so that the minutes cancel out. And now I just do the arithmetic here. 20 times 1 is 20, divide by 60. So that's 1/3 of an hour. Okay, so 20 minutes is equal to 1/3 of an hour. So the distance, okay, notice up here, right? The velocity is equal to the distance traveled divided by the elapsed time. Well, if that's true, then the distance traveled is equal to the velocity multiplied by the time. Okay, if you know any two of these variables, you can find the other one. So that's what we're going to do here. The distance traveled is equal to our velocity, 21 miles per hour, times 1/3 of an hour. Okay, units canceling here. So we get 7 miles. Okay, so keep track of those units. It's a good way to make sure that you're on the right track as far as your answer, right? We're trying to figure out distance, so it makes sense that we got miles for our units there. Okay, so that's a couple of linear velocity problems. Now, you're probably familiar with that concept already, so that hopefully wasn't too bad. Let's dive into angular velocity here. Okay, so we're going to do omega is equal to theta over t. Okay. Omega is equal to theta over t. Now, we're going to be measuring theta in radians. Okay, that's the angle in radians. Couple quick examples here. Find the angular velocity of a 45 RPM record. Okay, so these have kind of become a niche thing nowadays. Vinyl records are making a comeback. Now, the big ones are called long play albums, and there's a kind of a little record. When a record company wanted to release a single song, they'd put it on a 45, and it's called a 45 because the record player would have to rotate at 45 RPMs, 45 revolutions per minute, to play the record. Okay, so it tells us how many turns the record player makes every minute. Now we need to convert this to radians. Okay, so 1 revolution is equivalent to 2 pi radians. So 45 RPM would be equivalent to 90 pi radians per minute. Okay, so that is the angular velocity in the terms that we will be using it. Okay, so a lot of times how fast something is turning is given to us in revolutions per minute. We need to turn that into radians per minute. Now, the reason that we're doing that is there is a nice useful connection, okay, between the two concepts. Okay, if we go back to our work with arc length, we remember that the length of the intercepted arc is equal to r times theta. Okay, so if I take r times an angular velocity, that would be r times theta over t, right? Because that's what omega is. Omega is theta over t. Well, that would be equal to s over t, because r times theta is the distance that you've gone around the circle. So that is the linear velocity. Let's do a quick problem here relating the two. Find the angular and linear velocity of a person standing on the equator. Okay, so let me draw a couple pictures here to help us understand what's going on here. So we've got our Earth there, a sphere. The equator, of course, is a line going right through the middle of the sphere. Okay, so a person standing on the equator can be thought of as standing on the edge of a disk. Okay, if you imagine we cut the Earth at the equator. So we got the northern hemisphere and the southern hemisphere are separated by our cut. All right, now the radius of the Earth, as we've discussed in some previous problems, is approximately 4,000 miles. Okay, so this person is, we can imagine, standing on a disk, radius 4,000 miles. Now we know that the Earth does one complete revolution in 24 hours. Okay, so of course we're thinking about the axis going through like that, and the Earth turns about its axis. It takes 24 hours to make that happen. Okay, so the complete revolution corresponds to an angle of 2 pi radians. So 2 pi radians over 24 hours. So the angular velocity is pi over 12 radians per hour. Now, the linear velocity, well, we have this formula relating angular velocity and linear velocity. If my object is moving on a circle, and I know how fast that circle is turning, I multiply by the radius, and that'll tell me how fast the points on the edge of the circle are turning. Okay, so my linear velocity would be r times omega, which would be 4,000 times pi over 12 miles per hour. Okay, we can do a little bit of canceling, right? There's a 4 in this, that's 4 times 1,000, so we can cancel out with the 4 over there. 12 is 4 times 3. So 1,000 pi over 3 miles per hour. And if we want to, we can check our calculator here and crunch the numbers really quickly. 1,000 times pi equals, take that number and divide it by 3. So I'm getting approximately 1,047 miles per hour. Okay, so that is the linear velocity of a point on the surface of the Earth, and hence a person standing on the equator at that point. They're actually moving at 1,047 miles per hour. Okay, so the key thing is this concept of angular velocity and its connection to linear velocity. Linear velocity is distance traveled divided by elapsed time. Angular velocity is measuring how fast something is turning.